Hi everyone, so we are back and we are on to problem 2. So I'm looking at scandium oxide, very interesting material. I want to dope it. So this is my host, this is my impurity. So I want to dope my host with vanadium oxide, V2O5, in order to change the band structure, blah, blah, blah. So I could form cation Frankel, anion Frankel, and Schottky defects. Activation for the anion is 3.2, 7, Schottky 1.9. So I know that's the dominant intrinsic reaction. So let's draw our little slopes up here. I want to draw and label the concentrations of scandium vacancies. So natural log of vacancies of Sc. Scandium is Se203, so that's 3 plus, 1, 2, 3. So the natural log of the concentrations of these defects, 1 over T. We know, again, I'm going to be at high temperatures, that's going to be an intrinsic reaction dominated, and then same thing for here, and we want the diffusivity of scandium. So natural log, diffusivity of Sc, 1 over T, exactly, intrinsic, extrinsic, and there we go. So let's look at Schottky defects, and let's look at writing that reaction. So what does my reaction look like? Null, vacancy in scandium, 3 plus vacancy in oxygen, plus 2. So I know to charge balance that. I have 2 of these, I have 3 of these. That looks to be pretty good. Yep. Excellent. So that is my reaction. Let's write our actual electro neutrality equation. So what I'm going to do, put the charge in front, equals my negative charges, positive charges. I must have charge neutrality, 2. And now I could write my equilibrium reaction. So my equilibrium Ks equals exponential minus essentially G formation of Schottky over Kt, which is equal to the concentration of vacancies of scandium, Sc, 1, 2, 3. And I'm going to have that squared times my, again, it's products of reactants. So vacancy is oxygen, 1, 2. And then 3 here. So there we go. So I've got those reactions. Now, again, I want to write everything in terms of the concentration of my scandium vacancies, or vacancies of scandium. So I'm just going to plug in. So vacancy of Sc, 3 squared times. And so now I'm going to rewrite that. Oxygens is 3/2 times vacancy of oxygen. All that cubed equals exponential minus G formation of Schottky over Kt. So I could see that basically what I'm going to have is vacancy of scandium, 3. The 5th is proportional to exponential minus G formation of Schottky over Kt. I'm going to get rid of this, put it over here, take the natural log, get this. So my slope, the concentrations will just be minus G formation of Schottky over 5K. Now, what about my diffusivity? Well, my diffusivity of Sc is going to be equal to my jump rate, my squared, my F over 2D, and also multiplied by the concentration, vacancy of scandium, 3. So, no temperature term, no temperature term, no temperature term, no temperature term. There's definitely a temperature term here, because my jump rate is proportional to exponential minus G migration over T. So for my diffusivity, it's going to look like this for my intrinsic, minus G formation of Schottky over 5K, minus G migration over 3. So what about the extrinsic defect, you may be asking me right now? Well, let's go ahead and write that out. So I'm going to erase here. We have the solution that we wanted. Solution not only that we wanted, but we needed. So once we do this, now we are doping V2O5 into Sc2O3. Let's make sure that it's correct. Yep. So I need to have a vacancy of Sc, and that's going to be minus 3. So there we go. All right, I need to have that reaction. And I also need to put V substituted for Sc, so Vanadium is 5 plus, so scandium 3 to 5, so that's going to be a positive 2. So I also know I need 2 of these at least. So 2 will give me 4. It's not going to work. I think I'm going to actually need 6 of these and 4 of these, because then that gives me this. So if I do that, that's a vacancy. Again, that's a difficult one problem to look at. 15 oxygen X. And if I wanted to make 6, actually not 6, because we have 6 scandium, 4 scandium here. So that's 10, so 5. There we go. We got it. So the only thing left is my electroneutrality equation. So all I'm going to do is VSC 3 equals 2 VSC. Again, this is the substitutional cation. Again, that's a difficult problem. So in my extrinsic regime, my temperature is low. So I'm not going to have these dominant reactions that are formed from some enthalpy formation. So my concentration vanadium, scandium, vacancies is dominated or determined by how much of the substitutional cation is occurring. So I don't have any relationship with temperature here, but I do indeed have that migration term that carries over. So for the diffusion, the equation remains the same, but now I come from here. So that is it for number 2. We'll see you next time on our number 3. So see you then. Thanks. Bye.